AP Physics, this is your next lesson in the subject of circular and rotational motion. We're coming up toward the end of the course, and we're going to cover this subject before we get to our final day. So let's go. So we studied translational, which is the same as linear motion. When we studied it, we said forces are in equilibrium. That is, they're balanced when opposing forces are equal. So the 8 on the top and the 8 on the bottom of that free body diagram are opposing each other. The 12 on the right and the 12 on the left are opposing each other. And so those are balanced forces. Okay, so when forces are in equilibrium, the object can either be not moving or it can be moving at a constant velocity. That is the same speed and the same direction. An object that is not moving is in static equilibrium, and an object moving at a constant velocity is said to be in dynamic equilibrium. To create circular or rotational motion, there must be a force. A wrench is a tool used to tighten a bolt on a screw. So over on the left you see what's called a nut and a bolt, and you put that nut on there and it spins around, and usually it spins pretty easily until you get it to the point where you want to tighten it, and then you have to use something like a wrench or a pair of pliers to do that. In this case we're showing a wrench. So the pivot is the point around which the wrench turns, and we call that, the pivot is called the fulcrum. It can also be called the pivot. That's where the nut would fit inside of that little space there, and that's what you would turn. The handle of the wrench is called the lever arm. So to create circular rotational motion, there must be a force. And so a wrench is a tool used to tighten a nut or a bolt. And there you see one turning like that. So the handle of the wrench is called the lever arm. Okay, so there you see the wrench again, and that's how it turns. It would turn like that around the pivot, that open space on the top. And again, the handle is called the lever arm. So on a wrench, the fulcrum is at one end, and you can see that the arrow pointing to the fulcrum. It is not necessary for the fulcrum to be at the end. A seesaw has a fulcrum in the middle, so that's basically where the two children pivot around in their rotational motion. Okay, to make a wrench turn, a force perpendicular to the lever arm must be applied. So there you see a force pushing down at a 90-degree angle that's perpendicular to the lever arm. So the rotational version of force is called torque. The equation for torque is force times distance, the distance that the pivot is from where the force is applied. The units of measure for torque are Newton meters, newtons times meters. So tau is the symbol for torque. And then of course F is force, and D is the closest distance to the fulcrum, and that's the perpendicular force. So the amount of torque equals the force applied perpendicular to the lever arm times the distance from the fulcrum. So you remember when we were out and we were pushing the big heavy metal gate, and one student was pushing close to the hinges, and it took a lot of force, but the distance from the hinges, the pivot, was not very far. Then we had a second student pushing from farther away out at the end of the gate, and it didn't take nearly as much force, hardly any force at all to push it, but that student had to walk a farther distance in order to do it. So there's a trade-off between force and distance, and that's how torque works. It's not just a function of the force, it's a function of the distance from the pivot. So torque is the rotational equivalent of force. Example, what is the torque on the wrench below if a force of 8 newtons is applied 0.5 meters from the fulcrum? So there you see the situation right there. There's the formula. You simply plug in the numbers, and it's 8 newtons times 0.5 meters. So that would be a torque of 4 Newton meters. The convention simply means a generally accepted standard is for the counterclockwise torque to be positive and the clockwise torque to be negative. The same way we go around the unit circle when we deal with that. The force is applied at an angle to the lever, then the formula becomes force times distance sine theta. So you have to apply some trigonometry when you have an angle, just like with any forces we've dealt with in the past. So example, what is the torque on the wrench below if a force of 10 newtons is applied 0.75 meters from the fulcrum at an angle of 30 degrees? So you're saying that that is being pulled up at kind of an angle like that. So what would that force be? Well, the pure force is 10 newtons. But you're only interested in the component of the force that is that red dashed arrow that's pointing upward, because that's perpendicular to the lever arm. So you don't care about the force going laterally right and left. You only care about the up and down force here. So we're interested in the component of the force pointing upward as we look at the picture, the opposite side opposite theta, which is the sine of theta. So you use sine in these types of calculations. So this will indicate what part of the 10 Newton force is pointed in the direction the wrench will be turning. So we're assuming we want to turn that wrench upward. So it's tau equals 10 newtons times sine of 30 times 0.75 meters. And you notice that the sign is in a different place than in the formula above. It doesn't matter. It's a multiplication, so it all comes out the same. And tau equals 3.75 Newton meters. That's the amount of torque that you actually are putting on that wrench, is 3.75 Newton meters. The previous problem would be solved in the same way if the force had been pushing rather than pulling on the wrench. So there's the same formula, and you can see the same thing there. This time it's still a 30-degree angle, but it's pushing from the bottom on the wrench. It doesn't matter. It's the angle that it is. It's the component of that force vector, that 10 Newton vector, that's pushing upward. And so again, it's 10 sine 30. So there are three classes of levers, so we're just going to learn these just for nomenclature. They won't test you on this on the AP, but it's just to know the different types of levers. So whichever part, the fulcrum, load, or effort is in the middle of the lever indicates a class 1, 2, or 3 lever. So let's see what's meant by those terms. FLE is a way to remember the classes of levers. So there's FLE. So fulcrum, if the fulcrum is in the middle, it's a class 1 lever. If the load is in the middle, it's a class 2 lever. And if the effort is in the middle, that's basically your muscle power, what you're using to create the force to do the work. If that's in the middle, then it's a class 3 lever. So let's take a look at an example. A fulcrum is the stationary point around which the work is taking place. So the load is what the machine or the fulcrum is designed to move, and the effort is the force exerted to move the load. It's the muscle power or the machine power. So whichever part of the lever is in the middle of the lever indicates class 1, 2, or 3. So class 1 lever. On a class 1 lever, the fulcrum is in the middle. So that's the F in FLE. So if the fulcrum is in the middle, since F is the first letter in the word FLE, then that's a class 1 lever. That's an example of that is the seesaw. So the fulcrum is in the middle between the children. The girl provides the effort to cause the boy, he would be the load, to go up. And then they take turns, and similarly the boy would provide the effort to cause the girl, the load, to go up. A class 2 lever, on a class 2 lever, the load is in the middle. So that's the L in FLE. So since the L is in the middle of the letters FLE, then the load is in the middle, and that's a class 2 lever. So you see a man pushing a wheelbarrow. So on the wheelbarrow, the load is in the middle. That's the vegetables that he's carrying. The wheel in the front is the fulcrum or the pivot. And the man lifting the handles is the effort. That's the muscle power. So the thing in the middle of those three is the load. That's the L, so that's a class 2 lever. Class 3 lever, the effort is in the middle. So that's the E in FLE. So that's the last letter, so that's class 3. So in this case, the load is the snow that's being shoveled. The fulcrum is the girl's right hand. It's not going to move. She's going to move her left hand, but she's going to keep her right hand stationary. So that's the fulcrum. And then the effort, the work is actually being done by her left hand. That's what she's using. That's her muscle power she's using to lift the snow. So first class, second class, third class lever, just depends on whichever one is in the middle, the fulcrum, the load, or the effort. That determines whether it's class 1, F, class 2, L in the middle, class 3, E in the middle. Okay, and that takes care of our first lesson on torque. In our next lesson, we'll talk about some of the applications of torque.